Kubernetes is not a deployment tool. Cold open, the button that does not exist. Most people meet Kubernetes through a deployment. You give it a container image, ask for 3 copies, and 3 green boxes appear. So the obvious mental model is Kubernetes is a very complicated deployment tool. But that model breaks the first time a server dies at 3 in the morning, and Kubernetes creates a replacement without anybody deploying anything. Or when you change 3 replicas to 50 and dozens of independent machines quietly reorganize themselves. Or when you install an operator and Kubernetes suddenly knows how to manage a database, issue certificates, or repair a distributed system. There is no giant deploy button hiding in the control plane. Kubernetes is a collection of control loops. You describe the world you want. Kubernetes stores that description, compares it with the world that exists, and keeps making small corrections. Deployment is only one consequence of that machine. 1. 2 versions of reality. Imagine a cluster with 3 running copies of an API. On one side, we have desired state, 3 replicas, this container image, this amount of memory, and these labels. On the other side, we have actual state. Perhaps only 2 pods are alive. 1 node may be full. 1 container may be crashing. The 2 pictures do not match. A traditional deployment script usually performs a sequence of commands. Create this, start that, then move to the next step. If reality changes after the script finishes, the script is gone. Nothing is continuously asking whether its assumptions are still true. Kubernetes takes a different approach. Its objects are persistent records of intent. A control loop repeatedly observes the cluster, calculates the difference between desired and actual state, and acts to reduce that difference. The important word is repeatedly. If the first correction does not work, the loop runs again. If reality changes tomorrow, the loop runs again. Kubernetes is not executing a one-time recipe. It is maintaining an invariant over time. 2. The API is the center of the machine. When you run kubectl apply, the YAML is not sent directly to a worker node. It goes to the Kubernetes API server. The API server validates the request, applies admission rules, and persists the accepted object through Kubernetes backing store, etcd. That stored object is not a command like start container now. It is a declaration. A deployment named checkout should use this pod template and should maintain 3 replicas. This separation matters. Clients submit intent through one API. Control plane components observe objects through that API. They can watch for changes instead of every component inventing its own private communication channel. And etcd does not run your containers. The API server does not choose a machine. The YAML itself does not travel around issuing orders. The system moves because specialized controllers notice that stored intent and react. 3. A deployment is a chain of responsibility. Create one deployment with 3 replicas, and a surprisingly long chain wakes up. The deployment controller notices that the deployment has no matching replica set. Its correction is to create or update one. Then the replica set controller notices that the replica set wants 3 pods but has 0. Its correction is to create 3 pod objects. Notice what did not happen. The deployment controller did not shesh into 3 servers. It did not start 3 containers. It created another piece of desired state. Each controller owns a small problem. It watches a particular kind of object, compares desired state with observed state, and writes the next correction back through the API. That is why the architecture scales conceptually. A deployment handles rollout strategy. A replica set handles replica count. A job handles completion. A node controller handles node health. They cooperate through shared state without becoming one enormous orchestration function. The corrections also need to be safe to repeat. A controller may observe the same mismatch more than once. Instead of assuming my previous command definitely succeeded, it checks the latest state and reconciles again. 4. The scheduler does not run anything. Now 3 pod objects exist, but none of them has a node. This is the scheduler's narrow job. For each unscheduled pod, the scheduler finds nodes that are feasible. Does the node have enough requested CPU and memory? Do labels, affinity rules, taints, tolerations, and other constraints allow the pod to live there? Then it scores the feasible nodes and selects one. The result is a binding. This pod belongs on that node. The scheduler still does not start the container. It makes a placement decision and records it through the API. This is a useful debugging boundary. If a pod is pending with no node, look at scheduling constraints and capacity. If it has a node but the container cannot start, the scheduler has already finished its part. The problem is further down the chain. 5. The kubelet closes the loop on each node. Every worker node runs an agent called the kubelet. The kubelet watches for pods assigned to its node. When it sees one, it works with the container runtime to make the pod's containers exist and keep them running according to the pod specification. Now our declaration has crossed several boundaries. A human created a deployment. One controller produced a replica set. Another produced pods. The scheduler assigned each pod to a node. A kubelet asked a runtime to create containers. At the bottom, Linux processes finally run. But every step above them was driven by observed state, not by a single top-down deployment procedure. The same separation explains why the pod exists and the application is ready are different facts. Kubernetes can know that a container process started while a readiness probe still says the application should not receive traffic. Object existence, process health, and service readiness are different signals used by different loops. 6. Watch the machine repair itself. Now pull the plug on one worker node. At first, desired state still says 3 replicas. Actual state eventually reveals that one assigned pod is no longer available. The node and workload controllers do not need the original deployment command to come back. The declaration is still stored. Once the failed pod no longer counts toward the replica set's desired total, the mismatch returns. Wanted 3, available 2. The replica set controller creates a replacement pod. The scheduler places it on a surviving node. That node's kubelet starts its containers. Desired and actual state converge again. This is Kubernetes self-healing, but with an important qualifier. Kubernetes can only repair what you have described and what its controllers know how to observe. It cannot invent a correct readiness probe. It cannot guess safe database failover semantics. And a bare pod without a managing workload controller does not magically gain the same replacement behavior as a deployment. Kubernetes is persistent, not omniscient. 7. Why operators feel like magic. Once you understand control loops, Kubernetes operators stop looking mysterious. Kubernetes lets you extend its API with custom resources. You might create a database cluster object that says 3 database members, daily backups, and this version. By itself, that object is only stored intent. The other half is a custom controller, the operator, which understands what that intent means. It can observe the database, create supporting resources, rotate through an upgrade, or update status. Then it reconciles again. This is the same pattern as the built-in machinery. Add a vocabulary for a domain. Add a controller that knows how to move reality toward it. That is the real platform power of Kubernetes. It is not merely a place to run containers. It is a framework for building APIs backed by continuously running control loops. 8. A better way to debug Kubernetes. This mental model changes how you debug. Do not begin with, "Why didn't Kubernetes deploy my app?" Ask, "Which desired state object exists?" Which controller owns the next transition? What actual state did it observe? And where did reconciliation stop? Deployment but no replica set? Inspect the deployment controller and its events. Replica set but too few pods? Inspect quotas, admission failures, and the replica set's status. Pod exists but has no node? Inspect scheduler events, resource requests, and placement constraints. Pod has a node but no running container? Inspect the kubelet-facing conditions, image pulls, volumes, and the container runtime path. Container runs but receives no traffic? Inspect readiness and the service's endpoints. Instead of one giant black box, you now have a pipeline of ownership boundaries, each leaving evidence in the API. Payoff: Kubernetes is a promise under pressure. So yes, Kubernetes can deploy your application. But the deeper idea is that it keeps a promise under pressure. Machines disappear, containers crash, teams change replica counts, new controllers add new kinds of intent. The cluster never stays finished, so Kubernetes never really finishes either. It stores a desired world, watches an imperfect real one, and runs many small loops that keep closing the gap. Once you see that, the API server, etcd, controllers, scheduler, and kubelets stop looking like arbitrary complexity. They are separate parts of one feedback system. Kubernetes is not a deployment tool. It is a machine for reconciliation. And deployment is just what reconciliation looks like on day one. If this changed how you see Kubernetes, subscribe for more visual explanations of the systems hiding underneath everyday developer tools.